Hello guys, today I'm going to talk about nucleophilic substitution reaction and how I'm trying my best to make you understand. Then so please stay with the video till the end. So let's start. Let's start with the substitution reaction. What are the reactions called substitution reaction? Substitution reactions are those where species or reagent substitute or replaces another species or reagent of same kind from the substrate. When it is nucleophilic substitution reaction, that means a nucleophile substitutes another nucleophile. This reaction goes like this: nucleophile attacks and bond breaks in the substrate, and X is leaving along with the bond pair of electron. Now, let's check the types of substitution reaction. Firstly, SN1. This reaction goes in two steps. In the first step, the CX bond breaks and a carbocation and a leaving group forms. In the second step, we get a reaction between nucleophile and the carbocation, and we get the final product RNU. Here, the first step is slow and the second step is fast. While going to the SN2 reaction, in this reaction, a new bond formation between the substrate and nucleophile, and the bond breaking process between the substrate and the leaving group happens in the same time, like this. This kind of reaction also called concerted step reaction. Now coming to the SN1. In SN1, the slow step is very important. Why it is so? We will understand this with a real life example. Let's imagine you are taking a road trip from point A to point C. Now a point B is coming in between of point A and point C, like this. Let's say the distance between A to B is 10 km and the distance between B to C is also 10 kilometers. But the difference is in the road. From A to B, the road is very harsh and highly congested, while from B to C, the road is extremely good, like freeways or expressways. From A to B, since the road condition is very bad, you take some 40 minutes to go through. But from B to C, you are taking just 5 minutes to go through. Now suppose a friend of yours is waiting at point C and calling you over the phone, "Hey, where are you?" If you answer that you are at point A, you are starting right now, then your friend will get the feelings that, well, you will come within 40 to 45 minutes. But if you inform your friend that you are at point B, then your friend will get this feeling that at any moment you will reach at point C. So in reality, the journey determining time is within the A to B. Now one point I want you to note it down, that if you really want to improve your journey time, then you can do by improving the road condition from A to B. You will not have much to do in the road between B to C. Remember this point. In another example also about the feelings I am talking about, if two friends are earning, one is earning 10,000, another one is earning 10,020 per month, you will get literally the feeling that A and B having the same salary. Okay, this is like that. So coming back directly to the SN1 reaction, what are the species or entities are involved in the first step? That is the substrate in the left hand side of the arrow and the carbocation and the leaving group in the right hand side of the arrow, and over the arrow you have solvent and temperature. So since slow step already I mentioned as the rate determining step and only one species is involved in this step, so the term 1 in SN1 coming from here, you must remember this point, that why SN1 is 1. You then answer that since only one species involved in the rate determining step, that is why it is called SN1. Okay, now let's see the parameters. In these parameters we have substrate. Within the substrate we have alkyl and leaving group. Other than that we have solvent and temperature. If you increase the temperature, that means you are injecting more energy to the system. Injecting more energy means that will always facilitate the bond breaking process between carbon and the leaving group X. So temperature increases will always help to increase the rate of the reaction, but that is not always our priority, because scientists always want to do a reaction in room temperature or in a temperature as less as possible, means within the quite close to the room temperature range. So anyway, we will see how we can deal with the alkyl group and the leaving group and the solvent so that we can increase the reaction rate. Okay, now one point I want you to remember, that the substrate which is taking part in SN1 reaction, that substrate must have a dipole moment of, to be precise, a bond moment within the CX bond, where the delta plus must sit over the carbon and the delta minus must sit over the leaving group, so that will facilitate not only formation of R plus and X minus, that also will attract the delta plus end, also will attract the nucleophile. Nucleophile means what? Nucleus loving, means plus charge loving. If within the substrate, if you don't have any plus charge end, at least a partially plus charge end, then the substrate will fail to attract the nucleophile. Okay, so no matter it is SN1 or SN2, if the substrate is non-polar type, then that substrate cannot undergo in SN reaction. Now here, in just before 2 slides, I want to tell you that the electronic effects and steric effects I will consider, and in electronic effects the resonance effect you should give much more priority compared to the inductive and hyperconjugative effect. All these three effects will facilitate SN1 reaction, but the resonance is having the most priority. Anyway, here in this chart I have given many permutation and combination when the SN1 reaction can occur and when not. You please go through this chart. Now, while talking about the leaving group ability, there are few conditions I have given. Suppose in first condition I talked about if the leaving group when attached with the substrate having a formal positive charge over it, then it once it take the bond pair of electron, it will become neutralized, and this event itself will facilitate leaving group to leave the substrate. Compare to the that kind of leaving group which is attached within the substrate as neutral and with the bond pair of electrons, when it leaves as negative charge ion, that is not encouraging compared to the first case. So first case is better leaving. Now coming to the point number 2. Here the explanation has given based on the basicity term. So the point is the leaving group which is least basic will be the best leaving group. Now when you compare this kind of thing, you should try to keep the central atom of the leaving group same. Okay, you cannot compare H2O with NH3, okay, because the central atom gets different. But again, there also you can bring the basicity term, we'll see later. So here H2O is the least basic, then the ROH, which is again less basic than acetate, and acetate is less basic than hydroxyl ion. And in the third and fourth point, I explained this one based on the periodic table group and period situation. So along with the group, how the leaving group ability changes. So I have taken group 7 elements as reference, where we have fluorine, chlorine, bromine, iodine. Okay. So when they form anion, as we all know, iodide ion is biggest in size. So here the point is, the more the polarizability of the leaving group, best it will be as leaving group. Okay, what polarizability means? Polarizability means dispersion of the charge. More polarizability, more dispersed the charge is. So in case of iodide, the iodide having very big in size, and the single charge will disperse, will get more space to get dispersed compared to the bromide, that is again better than chloride. And since fluoride is the smallest, it is having the least charge dispersion ability, which is the polarizability is the opposite term of charge density. Charge density means charge per unit area. For fluoride, charge density is maximum, and for iodide, charge density is minimum. More the charge density, least the species stable. You should remember this point. Now if we consider along a period in the periodic table, the electronegativity of atoms increases from the left hand side to right hand side. Now the point is, more the electronegativity, it will able to grab the negative charge better. So in second period, if we take carbon to fluorine, fluorine is having the most highest electronegativity. So fluoride minus is more stable than OH minus, which is again better in better shape than NH2 minus. NH2 minus is more stable than CH3 minus. So leaving group trend also will follow in the same way. Now come to the solvent effect. While discussing the solvent effect, we should start with an example. Let's say CH3Cl is going through SN1 reaction. To break the bond between C and Cl, it needs 950 kilojoule of energy per mole when the reaction is carried out in gaseous state. Okay. Now, when the same reaction is carried out in water as solvent, the energy need reduced in a big extent to just 263 kilojoule per mole. Then the necessary question arises that what the magic H2O is doing so that the energy need becomes very less. Then come to this picture. Listen, initially when the heterolytic bond cleavage happens, because of opposite charging species forms, they are attached using the electrostatic attraction. This kind of attachment called intimate ion pair. So if the intimate ion pair is there, the problem with it is that the X minus can reattack on the carbon center of the carbocation and the Rx can reform. But in gaseous state, if we want to push each other apart, then we need to give some more energy. But if we use protic polar solvent, as you all know, protic polar solvents having a delta plus end hydrogen and delta minus end oxygen. So the delta minus end oxygen will envelop the R plus and delta plus end hydrogen will envelop the X minus and take the plus ion and minus ion away from each other. So that is why H2O helps and produce lot of solvation energy, and that again get utilized in the bond breaking process. While talking about aprotic polar solvent, here also some sort of dipole movement is there, but this is not very strong. So this kind of solvent can solvate the carbocation but cannot solvate the negative charge ion. So for SN1 reaction, since both the plus ion and minus ion forms, protic polar solvent are much better choice than aprotic polar solvent. Now coming to the steric effect, you should remember that all the substrate taking part in SN1 reaction are sp3 hybridized with the 109-degree bond angle theoretically. Now the substituents present R1, R2 and R3, if they are bulky, then they will feel steric congestion in this sp3 hybridization state. They will be happy to have more space to live. So if the hybridization changes from sp3 to sp2, then they will be very happy since they are getting 120-degree bond angle and more space. That is why if you look at the reactivity where my arrow is shaking, the tertiary butyl halide is better substrate than isopropyl halide, which is again better than ethyl halide, and least reactive is methyl halide. Now we will go that once the carbocation forms, what will be the stereochemistry of the final product once the nucleophile attacks the carbocation. Listen, the carbocation is sp2 hybridized already I said. That means the pz orbital is out of the hybridization. Now the molecular plane if stays on the xy plane, then pz orbital will orient itself over the z axis in the perpendicular from the xy plane. Now the pz lobe will be oriented both side of the above the plane and below the plane of the xy plane. When the nucleophile comes to attack, it can attack or it can donate its bond pair of electron either from the top side or from the bottom side with 50-50 chance. That is why if we start with enantiomer pure substrate, we always get a racemic mixture product with 50% plus form and 50% minus form of the enantiomer. Now, for having more clarity, we will see couple of examples. In each case, we will compare the left hand side with the right hand side. So in the first example, we will compare A and B. If you look at A, once the carbocation form in the carbon where my arrow is shaking after chloride leaves the substrate, oxygen is sitting just beside it, and we know oxygen is having lone pair of electron which can donate it resonatically. This kind of facility is not available in the compound B since oxygen and the carbocationic carbon is apart. In between them one extra carbon came, and indeed we will get here one we will get minus I effect of the OCH3 group. Now if we come to the second example, first is allyl chloride, which once carbocation forms the double bond migrate and we can get two resonating structure. While in D, triphenyl methyl chloride, once carbocation form, that positive charge can distribute in all the phenyl ring and we get total 10 canonical form of the resonating structure. So D is better for SN1 reaction. Now in third example, if we compare tertiary butyl chloride and tertiary butyl bromide, as we know, for bromide ion, polarizability is better than chloride ion, means bromide ion is better leaving group. That means F is better for SN1 reaction than the E. Now coming to the G and H, both the cases substrate is same, the difference is in solvent. First one is water, second one is acetone. Here also we know the particular solvent is better for SN1 reaction, so G will work better. Now see another type of reaction called SN1 prime reaction. Here allylic rearrangement take place. So once the carbocation form, the double bond migrates and the plus charge can shift from 1 carbon to the 3 carbon. Now if we introduce one nucleophile, here I have shown OH minus. So OH minus can either attack 1 carbon or 3 carbon. So when it is attacking 1 carbon, we will say that SN1 reaction. When it is attacking third carbon, then we can say that SN1 prime reaction. In next video, we will talk about SN2 reaction. So please subscribe if you like this, and please click on bell button so that you can get future notification. Thank you.